So we've got a right triangle drawn over here where this base's length is A, the height here is B, and the length of the hypotenuse is C. And we already know when we see something like this, we know from the Pythagorean theorem the relationship between A, B, and C. We know that A squared plus B squared is going to be equal to the hypotenuse squared, is going to be equal to C squared. What I want to do in this video is explore how we can relate trig functions to essentially the Pythagorean theorem. And to do that, let's pick one of these non-right angles. So let's pick this angle right over here as theta. And let's just think about what the sine of theta is and what the cosine of theta is, and see if we can mess with them a little bit to somehow leverage the Pythagorean theorem. So before we do that, let's just write down SOHCAHTOA, just so we remember the definitions of these trig functions. So sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And TOA, tan is opposite over adjacent. We won't be using tan, at least in this video. So let's think about sine of theta. So sine of theta, I'll do it in this blue color. So sine of theta is what? It is opposite over hypotenuse. So it is equal to the length of B, or it is equal to B. B is the length. B over the length of the hypotenuse, which is C. Now, what is cosine of theta? Cosine of theta, well, the adjacent side, the side of this angle that is not the hypotenuse, it has length A. So it's the length of the adjacent side over the length of the hypotenuse. Now, how could I relate these things? Well, it seems like if I square sine of theta, then I'm going to have sine squared theta is equal to b squared over c squared, and cosine squared theta is going to be a squared over c squared. It seems like I might be able to add them to get something that's pretty close to a Pythagorean theorem here. So let's try that out. So sine squared theta is equal to b squared over c squared. I just squared both sides. So over c squared. Cosine squared theta. Cosine squared theta is equal to a squared over c squared. So what's this sum? What's sine squared theta plus cosine squared theta? So sine squared theta plus cosine squared theta. Cosine squared theta is going to be equal to what? Sine squared theta is b squared over c squared. B squared over c squared plus a squared. Plus a squared over c squared. A squared over c squared, which is going to be equal to, well, we have a common denominator of c squared, and the numerator we have b squared plus a squared. B squared plus a squared. Now what is b squared and plus a squared? Well, we have it right over here. Pythagorean theorem tells us b squared plus a squared, or a squared plus b squared, is going to be equal to c squared. So this numerator simplifies to c squared, and the whole expression is c squared over c squared, which is just equal to 1. So using the SOHCAHTOA definition, and in a future video we'll use the unit circle definition, but you see just even using the SOHCAHTOA definition of our trig functions, we see probably the most important of all the trig identities, that the sine squared theta, sine squared of an angle, plus the cosine squared of that same angle, I'm introducing orange unnecessarily, plus the cosine squared of that same angle is going to be equal to 1. Now you might probably say, okay, Sal, that's kind of cool, but what's the big deal about this? Why should I care about this? Well, the big deal is now you give me the sine of an angle, and I can solve this equation for the cosine of that angle, or vice versa. So this is actually a pretty powerful thing, and this is also part of the motivation even for the unit circle definition of trig functions.